Welcome to my presentation. Today I'd like to talk about the fascinating connection between topology and quantum computers. Actually, topology is a branch of maths that explores the properties of objects and how they can transform without changing their fundamental characteristic. It allows to understand the underlying structure and relationships between objects in a unique way. To give you an example, consider a donut and mug. At first glance, these objects may seem completely different. However, from a topological perspective, they are equivalent. How this is possible? It's because both the donut and the mug have one hole. Regardless how we stretch, move, or alter their shapes, they retain this fundamental property of having only one hole. And topology helps us see beyond the surface appearance and uncover deeper connection between seemingly unrelated objects. Now you might be wondering, what does this have to do with quantum computers? Well, just as topology allows us to understand fundamental properties of objects, it can also provide us with a powerful tool for designing and building quantum computers. They require flexibility to handle fluctuations and environmental change while maintaining the integrity of their computations. This flexibility is crucial for overcoming the inherent challenge of working with quantum systems. One of the challenges in quantum computing is delicate the nature of subatomic particles, like electrons. They can easily decohere or disrupt by movement of fluxions. However, in 2016, physicists made a groundbreaking discovery. It stemmed from the quantum Hall experiment. In the quantum Hall experiment, a two-dimensional electron gas named 2DEG is formed at the interface of two semiconductor layers under, inter, under the influence of magnetic field. This 2DEG exhibits the quantum Hall effect, where the perpendicular to magnetic field and causes electrons to occupy quantized energy levels and resulting in a specific conductance patterns. And then the experiment revealed something remarkable. Despite the magnetic field, the electrons remained unchanged. However, altering that field led to phase change or alterations in the electron state. This challenged our previous understanding of subatomic particles and opened up new possibilities. The experiment showed that under certain conditions, vortex-like currents of electrons called vortices can form. These vortices exhibited unique properties, particularly as temperature changed. Interestingly, they conducted electricity in a consistent manner, providing a promising avenue for creating qubits that can retain information and withstand computational change. To achieve this, qubit systems with interchangeable vortices are employed, and this is where a special type of particle comes into play. Now let's delve deeper into the fascinating world of Majorana fermions and non-abelian anyons. While it is true that the existence and properties of anyons are still being investigated, they hold immense potential in the field of quantum computing. Majorana fermions are special quasi-particles that exhibit characteristics of both fermions and bosons. They represent half an electron and exist in a constant state of creation and annihilation. In the context of quantum computing, Majorana fermions are theorized to be positioned at both ends of superconducting material. with braided electrons in the middle. The interplay between Majorana fermions and braided electrons gives rise to formation of non-abelian anyons, which are particles capable of changing their quantum states by switching places. These anyons, when braided together in qubit system, can encode and manipulate quantum information. Now let's discuss the immense potential and how it can revolutionize the field of quantum computation. They are inevitable, offering exponential computational power. However, to make them practical, we must develop fault-tolerant quantum computers that can withstand local noise and errors. And topological quantum computing harnesses the unique topological properties of electrons to create robust quantum computers. By utilizing quasi-particles known as Majorana fermions, topological quantum computing takes advantage of their spatial characteristics. When Majorana fermions interact within two-dimensional superconducting materials, they give rise to particles called anyons. These anyons play a crucial role in quantum computation. In topological quantum computation is performed by manipulating anyons, which change their states by swapping places. These anyons are braided together within qubit systems, forming intricate patterns, and the remarkable property of braids is that they hold quantum information, which remains unaffected by local noise. This property, known as decoherence, ensures the integrity of quantum informations. However, it's important to note that further research is still needed to solidify the existence and characteristics of anyons, advancing our understanding and enhancing the potential of topological quantum computing. Thanks for listening.